So the conceptual question is actually part of two of them, so that I can get you to try to see some understanding about how all of this really, fits together. So the first one that we want to do is that I need to set up a situation, and I could imagine that I have a hill, maybe something, let's do this, something like this. And this is a grassy area. And this grassy area is part of a cliff. Okay. And then this guy leads into a water where you have some type of lake or river or whatever it is that you want to think about here. And what we want to do here is that we could imagine that we have a tree. Okay. So I could imagine that we have a tree. And in this tree, there's a branch. Let's say that this is a branch right here. And I could imagine that we have a person standing right here. And attached to this is that there's a rope. So let's imagine that I have a rope that I've lassoed onto here. And it's attached right there. So the question is, as this person jumps off this cliff, they can swing, and they could swing along a path that goes like this. Let me draw this a little bit different because I need to, let me make an arc here. Yeah, something like that. So now what you're seeing here is that one of these paths you can take is that you can fall right down in here. And I'm going to call this path number 1. And then there's going to be a second path where this person can then do the following thing. They can also let go right here, and they take another path that goes and they fall into the water like this. And this is going to be path number 2. So what is my question here? So this person is going to fall. They can let go at the rope right here and take path 1, or they could let go right here and take path 2. So the question is, which path how do I say this? Which path has the higher speed upon entering the water? So how do I deal with this thing here? So the way I deal with it is that first I have to talk about energy. So what do I know about the energy here? So the way the energy works is that I have to talk about my system. That's a big deal. So here we go. So I'm going to make this my system. And in this system, do I want to include Earth or not? And I would say that you should include Earth. So I'm gonna choose my system to be the person plus Earth. So now the question is, what are the external forces? So in other words, look at the force of gravity. The force of gravity is now internal. So are there any external forces? And the answer is yes. And what's it going to be? It's the force of the rope. So what do I know about the rope here? So if I look at the path, look what happens here. So if I look at a circular path, what's going on? If I pick one particular point along this path, here's what I'm going to find. That there is a tension force. You know what? I don't like this being an orange. Let's give this a different color. So now here's what you're going to see. The tension force is going to be in this direction here. But now look at the displacement. The displacement at that point is perpendicular. If I pick another point, note that the tension force is going to be seeking the center, but then the displacement at that point is going to be perpendicular. So that means that the work of the tension, because they're always perpendicular, we then say that the work of the tension is always zero. So when I look at this thing, if I look at the net work, it's going to be the work of the tension, but the work of the tension is always going to be zero. Therefore, the change in mechanical energy is zero, which then implies that the mechanical energy at 1 is equal to the mechanical energy at 2. So let's draw a bar diagram. So using a bar diagram, which one has the highest kinetic energy upon entering the water? So now let's set up our points here. So what I'm going to do here is that I'm going to take this and I'm going to copy this again, and I want to transfer it down below because we want the bar diagram to be nice and clean. So here I go. So I can get rid of all this stuff because we now know that's the case. So when I'm looking at this thing, what do I actually see here? What I see here is that I'm assuming that this person is essentially going to fall. We don't have to make that assumption. We could give it kinetic energy. In fact, let's give it a little bit of kinetic energy. So I'm going to set my height here to be 0 at this point. So then that means here is that this is my y equal to 0 point. So now, here we go. This guy starts off with some gravitational potential, and let's call this point 0. Then we're going to call this point 1 here, and we'll call the other one point 2. So this is the gravitational potential energy at 0, and we're going to say that when he jumps off, he starts off with some initial kinetic energy. Because mechanical energy is conserved, we know that that has to be a constant. So now let's look at path 1. At path 1, how much gravitational potential energy does he have at path 1 when he enters the water? 0. UG1 is 0. We have no choice but to conclude that all of that got to convert it into kinetic energy, K1. Now, if I look at point 2, how much potential energy is at point 2? According to this, it has to be 0 as well. So we are forced to conclude that the kinetic energy right here must also be that height. So without doing a single calculation, we can conclude here that K1 must be the same as K2. So therefore, the velocity 1 must be the same as velocity 2. So both paths cause the same entry speed into the water. Look how important conservation of energy made it easily to answer this question right here. Okay, that's one that I want to look at, and I want to look at one more. And this one is actually part of the PLC. And I think that this is an important one. But this was not accounted for because I couldn't get solutions to the tutors in order for them to check off, PLCs anymore. And so therefore, I just didn't make it a requirement. So the one thing that we want to look at is we want to look at this image right here. Here, let me grab the image of the PLC to make it a little bit easier right here. And this is just the beauty of a question. And here's what the question is right here. It says, 3 balls of equal mass are fired simultaneously at equal speeds from the same height above the ground. In other words, let's set up our situation again. Let's set up an image where, again, we have some grassy hill. And on this grassy hill, we're going to shoot 3 balls. And the reason how we're going to shoot them is that we have a platform right there. And we have the ability to shoot the ball 3 different ways. And the way I'm going to do this is that I'm going to color code each situation. So I'm going to say that here, I'm going to call this ball 1, and I'm going to shoot this with the speed of V1. And then I'm going to have ball 2 here at the same height. I'm going to shoot it with the speed of V3 here. Oh, no, I can't call that. Let me do that differently because 2 is down. And then I'm going to shoot this at V2. And then I'm going to have one more which is ball 3, and I'm going to shoot it at V3. Now, the only thing we know about this whole situation is that there's a couple of things. They all start off with the same height. And down here, we're going to set y equal to 0. And the other condition here is that the condition that the question says here is that this is V1 is equal to V2, which is equal to V3. So now the question says, rank in order from largest to smallest their speeds V1, V2, V3 as they hit the ground. So now what we want to do, of course, is that we want to talk about what? What is our system here? And of course, we always want to include Earth into the system. So when I choose my system here, I want the ball plus Earth to be part of the system. So when you look at kinetic energy, what you find here is that the velocity is independent of horizontal or vertical motion. And one thing that we can look at here is that what we find here is that kinetic energy is independent of angle. It doesn't depend on the angle at all, and only depends on speed. So then I can draw the bar diagram. So then check this out. This is 1, 2, 3. So if I take my objects here, I'm going to say that each of these balls are starting at the same height. So this is going to be the gravitational potential of 1, the gravitational potential of 2, the gravitational potential at 3. Now, because these balls are shot up with the same speed, they must have the same kinetic energies. So what this is telling us is that then K1, K2, and K3 must be the same. In other words, each of these balls all have the same kinetic energy. So when you start to look at these guys, what are you actually seeing here? Each of these then are equal to each other. And because they're equal to each other, then that means when these objects hit the ground, at some point down here, their gravitational potential is going to be 0. And all of this energy has to be converted into kinetic energy. So the fact that each of these start with the same height, start with the same kinetic energy, that tells me then that, so since each ball ends with the same final kinetic energy, their speeds must be the same. So V1 is the same as V2, which is the same as V3. And you know what? This is shocking. And the only reason why this is true here is kinetic energy is independent of angle. And a couple of things that I want to say here is that it was unexpected that I was going to have knee surgery and you were going to be put into a position where you suddenly signed up for a course to be online instead of face-to-face. Now, my experience with COVID teaching is that makes it a lot harder on you. So when I go and I do the grading for this course, I'm going to have that very much in mind. And I'm going to treat this to a large extent as an online course, which is different than a face-to-face. And so note that I expect that I am going to be easier on the grading as well as being easier on the grading, on giving grades, so that, should you be stressed? Yeah, I think you should always be stressed about when you take exams because I want you to do your best. But note that I'm very well aware that you got put into a very particular situation. So just know that. Once again, I've already apologized multiple times. I'm sorry that my health, my knee had to go south on me right before I started teaching. If I knew what I was going to endure, I would not have taught at all this semester and I would have taken a leave of absence. But, that's the past. There's nothing I can do about that. So the exam is due tomorrow by midnight. There are 5 problems. 2 are going to be on impulse and momentum. 2 are going to be on work energy or conservation of mechanical energy. And you'll be able to see that both questions can be answered by one of those 2 methods. And that's why, as I said earlier, you have options of how you solve that problem for problems 3 and 4. For problem 5, you're going to see here is that there is a situation where I believe you have 4 questions, 2 from impulse and momentum, 2 from work and energy that you have to answer, and you got to pick 3 of them. For the final exam, I will definitely have office hours, and I will definitely put up a practice exam where I have video links so that you can actually see the video and the solution. I see that there's 2 chat questions. The PLC 6 and 7, are they optional? At this point, yeah. I mean, would I do them? Yeah, I would do that. But that's, but I'm not going to hold you accountable and I'm not going to grade you for that. But I just want to make that. Yeah. Thanks, Teal. But I'm going to be, if you're taking Physics 4A next semester, there's none of it will be online. That's a guarantee. I hate online teaching, but unfortunately, that's the best that I can do. So come by and see me. I've been by myself in office hours. I would love to hang out and talk with you because otherwise I have freaking cabin fever because I can only move essentially between 2 rooms. Okay, thank you. I appreciate it. And I'll talk to you soon, hopefully. Okay, bye.